All right, hi, year 11s. This is Mr. Lim here, and this is another video on rates of reactions. And this time we're going to be talking about measuring the rate of reaction. Okay, so what does that mean? So we're going to be learning about measuring rates of reactions. We're going to be able to identify from chemical equations of possible substances that can be indicators of a rate of reaction. Okay, and we'll go through that. Describe some ways to measure the rates of reaction. Okay, so describe some ways. Determine the appropriate units for rates of reactions, just looking at the units of those, and then interpret some graphs as well. Okay, so that's going to be a pretty big one as well. So let's go through. Okay, so identify from chemical equations possible substances that can be indicators of rates of reaction. So rates of reactions can be measured by the consumption of a reactant, or the production of a product. Okay, so effectively, that's how you measure it in terms of you either see how much is consumed or how much is produced per unit time. Sometimes these two things are not visible, all right, or are not visible or measurable. Okay, so sometimes these reactions, like a acid plus a base, where the hydrogen ions and the hydroxide ions go together, that reaction there isn't really visible. Okay, so even though this is occurring, you can't see it, you can't measure it. Or actually, you can measure this one, but there are some reactions that aren't visible nor measurable. So therefore, we need to find something that is visible or measurable, and therefore use that to measure the rate of reaction. Okay, so what are some examples of visible changes for, oops, that's not what I wanted. Undo that. What are some visible changes that we can use? We can talk about the production of a gas. Okay, so the bubbles are forming. Okay, and you've seen that in a couple of reactions. But if you collect those bubbles and you can actually measure the amount of gas that's produced, which means that it's quantitative as well as qualitative, right? You can talk about a change in color. So maybe you use an indicator of some sort, or your reactants are actually a certain color, and they change color, and therefore that is a way to measure that rate of reaction. You can measure the dissolving of a solid, okay, and this is generally only qualitative because you can just see when it dissolves or see how fast it dissolves. You can't really measure that very well, right? Mass loss due to a gas loss. Okay, so in other words, you're producing a gas and that's changing the mass of the container holding the reactants, and so therefore that can be used as a way to measure the rate of reaction. You can do a pH change, which is only quantitative, not really qualitative, because you can't see that, right? So you just get a pH meter and you see what the pH is after X amount of time, and then again after another X amount of time, so on and so forth. Or you can look for the production of a solid, like a precipitation reaction, things like that. That can be qualitative and sometimes quantitative if you do it right. Okay, so you need to be able to look at a chemical equation and tell which reactants and products can be used in measuring a rate of reaction. Okay, so you're going to be looking for the production of solids, production of gases. Generally, those two are useful to pick out. Okay, so what's that? Gases. You're looking for gases. You're looking for solids. You're looking for H plus ions, which means that you can measure the pH, things like that. Or you're looking for information about whether the substances are colored. Okay, those are the things that you're looking for to work out, okay, I could use that one to measure the rate of reaction. All right, so what are some ways then to measure the rate of reaction? So this is talking about quantitative data. All right, so measuring the rate of reaction can be done in a number of ways. You can make multiple measurements over time. Okay, so you check how much gas is produced at 20 seconds, at 30 seconds, at 40 seconds, at 50 seconds, so on and so forth. Okay, so you change that volume of gas over time. You can see the change in pH over time. So what's the pH at time 10, at time 20, at time 30? Or you can even do conductivity. So see how if the presence of ions is increasing or decreasing over time, then your conductivity is another way to measure that rate of reaction. Okay, so that's possible ways to measure rates of reactions if you're measuring multiple measurements over time. Alternatively, you can just make one measurement and time how long it takes. Okay, so that might be something like, okay, well, I know that this reaction is going to go from purple to colorless, right? So how long will that take? Okay, so let's just time it. So we add them together, start the timer, and then we see how long it takes to go from purple to colorless. Okay, sometimes it'll be fast, sometimes it'll be slow. So you can be looking for distinct color changes. You can be looking for something to go opaque due to a solid forming. And even you can even say, okay, well, let's find out how long it takes for something to be produced or some certain value to change, like the 100 mils of gas. Okay, so if you're producing gas, instead of measuring it at 20 seconds, 30 seconds, 40 seconds, you could just say, okay, well, let's see how long it takes for it to get to 40 mils or 100 mils of gas to form. Okay, and that is then you can just use say that, okay, then I'll just watch it as it produces gas, and then, okay, it's made 100, that's how long it took, and then you can compare that against other conditions. Okay, so those are the different ways to measure the rate of reaction. Either measure it multiple times or just once. Okay, so now we're going to go into look at the units for rates of reaction. So the data gathered will affect how you report it, not only the unit, but also the way that you show it. Okay, so the appropriate units will depend on what you're measuring. So maybe you're measuring the amount of gas produced. So that might be mils or liters per minute or per second, or it might be grams gained or lost, things like that. And alternatively, it could be color change. So it might take the unit might not even be; it just might be seconds because it would be the time taken for a color change to occur. However, the data that is gathered in two different ways will affect how you report the rate of reaction. Okay, so if you are doing multiple measurements over time, you're going to try and do this in a line graph. So time as the horizontal axis, time here, and whatever, maybe you're doing volume or mass. Okay, and so you're going to end up with a line showing the rate of reaction. Okay, if you wanted to work out the rate of reaction at any given point in time, you can solve, or you can try and work out the gradient at that point in time. Okay, so the gradient at those points in time is the rate of reaction. Okay, so the gradient is the rate of reaction. Okay, so that's the steepness of the curve. You're not going to be asked to, I mean, you could be asked to work out the rate of reaction, and you just need to remember how to draw tangents to lines. Okay, so here's your curve, here's your tangent to the line, and then you can just do your rise over run to work out that gradient. But it's unlikely that's going to happen. All right, so once you have the gradient, you can have the independent variable versus your gradient as another graph, which will show your concept if you're doing this in investigation. Okay, your independent variable versus gradient at certain times to be shown. Alternatively, you might even just have different reactions occurring on the same graph. Okay, so you might have two or three different reaction conditions on the same graph showing different things. Okay. Alternatively, if you're talking about the time taken for a change to occur, so that's, remember, how long did it take to make 100 mils, or how long did it take for it to go opaque, your results can be compared to each other because they're just going to be time units. And so therefore, you can have the independent variable versus your result, which is like a unit of time, which can be shown saying, okay, well, at this concentration, it took this long. At that concentration, it took that long. And then you can just put those against each other. All right. So what that might look like is something like this. Here's your scale. So down a bit. So you might have concentration down here and then time here. So at a low concentration, it took a short, oh, whoops, that's the wrong way around then, isn't it? Okay, at a low concentration, it should take a long amount of time. At a high concentration, it should take a less amount of time. And therefore, this is the relationship between rate of reaction and the thing. The gradient there is not the rate of reaction. Each individual variable here is the rate of reaction, okay? That time there would be the rate of reaction there. Okay, let's move on. So interpret rate of reaction graphs and concentration and volume time graphs. This is the most important part because this is the part that will come up the most. Okay, so rate of reaction graphs can tell you various pieces of information, so not just the rate of reactions, okay, about the reactions. Number one, you can find out the rate of reaction via the gradient, but you can also find the relative amounts of reactants depending on the initial and final amounts. Okay, what does that mean? Let's have a look at a couple of graphs here. Okay, so this one here is a time versus volume graph. okay? And they're measuring CO2, so they're making CO2. You notice that this is in cms cubed. That's also another unit for mils, okay? And this decimeter cubed is effectively per liter. So this is showing at 1 mole per liter versus 2 moles per liter. And 100 centimeters cubed is 100 mils, okay? So it's showing you a couple of things. First of all, the gradient of this blue line here is much steeper than the gradient of that line. Okay, so the two gradients show that the blue line is having a faster reaction rate than the red line. Okay, but not only is it showing that the blue line is at a faster reaction rate, it's also showing by the position at the end that there's many more liters of CO2 produced with the blue line than with the red line, which means that there's actually many more moles of reactants. Okay, because the moles of reactants determines how much is produced, and the concentration determines the gradient. Okay, because you can have something that has a large gradient but then finishes quite quickly, or you can have something that has a low gradient that continues to go on. Okay, so you might have something like this. Watch this. Okay, so here's another line. Okay, like this. That shows that the green line compared to the red line, okay, had a much higher gradient, but it ended up at the same point. Okay, and if it ends up at the same point, that means they have equal numbers of moles. Equal moles. Okay, let's move on. Okay, here is another one. Okay, so again, this is what we talked about. All these three have equal moles. Equal moles. But they're at different rates of reaction. Which one's going at the fastest rate of reaction? A is it going at the fastest rate of reaction because it has the steepest gradient at the beginning. Okay. Let's have a look at another one. Okay. This is a very poor diagram. Okay. I included this one because I wanted to show you and see if you can work out why it's a poor diagram. Okay. What it's saying is that here is 0.5 moles per liter, 1 mole per liter, and 2 moles per liter. And the idea is that if this was actually 0.5 moles per liter and 1 mole per liter and 2 moles per liter, it means that they would all have to have different volumes. Okay? Because what it's showing is that they all end at the same point, which means that they have the same moles. If they all have the same moles, but they have different concentrations, they have to have the same different volumes. So N is equal to CV. All right, they have different of these. They have the same of that. Therefore, the volume must be different, which is a bit odd for a experiment. So this is a poor one, but that's what it would have to be. Might have to be 200 mils of this, 100 mils of this, and 50 mils of this. Okay, so that would be an unusual experiment. Okay, so let's go look at the last one, I think this is the last one. Nope, it's got one more. Okay, so here's another one. So looking here, which one has the greater rate of reaction? The red one, because it's got a steeper gradient. But look here, they end up at different places. So the blue one had more moles than the red, but the lower number of moles means that the lower number of moles doesn't stop it from reacting faster. Okay, so gradient is the speed of the reaction. The end point of it is the number of moles. Okay, then let's have a look at the last one. Okay, so here we have an uncatalyzed reaction in the red. Okay, then my question might be which one of those is showing a catalyzed reaction with the same reactants. Okay, so if they're the same reactants, they have to end at the same place, which means that it's probably this one. And because A does have the faster rate of reaction, that means that that's very likely to be the catalyzed reaction. Okay, all right. B might be a catalyzed reaction, but it also could be an increase in temperature, an increase in concentration. Unlikely to be increase in concentration because it actually has less of the stuff there. Does that make sense? So that it probably isn't going to be an increase in concentration, right? But but that's what it could be. So B has less moles than the uncatalyzed reaction, but it went faster than the uncatalyzed reaction, which means it might have had be done at a high temperature, but with less number of moles. Okay, and then again, C has much less moles and a much slower reaction, so therefore it might be uncatalyzed and colder, and there's less of it. Okay, so those are the ideas there for measuring rates of reaction. Sorry if this has been such a long video. We'll get a nice short video next time. Adios.